Look up at the night sky on a clear evening and you'll see thousands of points of light scattered across the darkness. Each one of those tiny pinpricks represents something almost incomprehensibly vast and powerful. Stars are not the small, delicate objects they appear to be from our earthly vantage point. They are massive spheres of plasma, each one a seething ball of superheated gas held together by the immense force of its own gravity. To truly understand what a star is, we need to think of it as nature's most impressive power plant, a cosmic furnace operating on principles that took humanity millennia to discover and understand. At the heart of every star, conditions exist that are so extreme they defy everyday experience. Temperatures soar into the millions of degrees. Pressures become so intense that the very atoms themselves are transformed. Within this hellish environment, hydrogen atoms are forced together with such violence that they overcome their natural repulsion and fuse into helium. This process, called nuclear fusion, is the same reaction that powers hydrogen bombs. But in stars, it occurs in a controlled, sustained manner that can continue for billions of years. Every second, our own sun converts approximately 600 million tons of hydrogen into helium, and in doing so, releases energy equivalent to trillions of nuclear weapons. This might sound like an unsustainable rate of consumption, but stars are so massive that they can maintain this process for incomprehensible lengths of time. The energy released by fusion doesn't simply vanish. It radiates outward from the core, traveling through thousands of miles of dense stellar material before finally escaping into space as the light and heat we observe. This radiation pressure, pushing outward, creates a delicate balance with gravity, which pulls everything inward. This equilibrium is what keeps a star stable. Too much fusion, and the star would expand and potentially blow itself apart. Too little, and gravity would cause the star to collapse. For most of a star's life, this balance remains remarkably stable, allowing stars to shine steadily for vast periods of time. The plasma that makes up stars exists in a state of matter we rarely encounter on Earth, where atoms are stripped of their electrons due to the intense heat, creating an electrically charged soup of particles that responds to magnetic fields and generates currents of energy throughout the stellar body. But stars don't simply appear fully formed in the universe. They have origins, moments of birth that occur in some of the most visually stunning environments the cosmos has to offer. Throughout the galaxy, vast clouds of gas and dust drift through the interstellar medium. These nebulae, as astronomers call them, can stretch for dozens or even hundreds of light years across space. They might appear serene and static in telescope images, glowing with ethereal colors against the black backdrop of space. But within these clouds, the seeds of new stars are constantly being planted. The gas in these nebulae consists primarily of hydrogen, the most abundant element in the universe, along with helium and trace amounts of heavier elements. The dust particles are equally important, made of carbon, silicon, and other elements forged in previous generations of stars. Something must disturb these clouds to initiate star formation. Sometimes a nearby supernova explosion sends a shockwave rippling through space, compressing regions of the nebula. Other times, the gravitational influence of passing stars or even collisions between gas clouds can trigger the process. Spiral density waves in galaxies can also compress gas clouds as they pass through. Whatever the trigger, once a region of the cloud begins to collapse, gravity takes over. As the gas falls inward, it heats up, and the collapsing region begins to spin faster, much like an ice skater pulling in their arms. This creates a rotating disk of material with a dense core at the center. The core continues to grow as more material falls onto it, and as it grows, it becomes hotter and denser. Eventually, after perhaps a few 100,000 years of collapse, the core reaches a critical threshold. The temperature and pressure at its center become so extreme that hydrogen nuclei begin to fuse into helium. At this moment, a star is born. The onset of fusion marks a transformation from a collapsing protostar to a genuine star generating its own energy. The new star's radiation begins to push back against the infalling material, eventually clearing away the surrounding gas and dust. Young stars are often obscured by their birth material, visible only in infrared light that can penetrate the dust. As they mature and their stellar winds blow away the remnants of their natal cloud, they gradually become visible in optical wavelengths. Many newly formed stars also create spectacular jets of material, beams of gas and plasma that shoot out along their rotation axes at tremendous speeds, creating glowing shockwaves when they slam into the surrounding nebula. Once a star has established fusion in its core and cleared away its birth material, it settles into the longest and most stable phase of its existence. Astronomers call this phase the main sequence, not because it represents some sort of progression, but because when scientists first plotted stars by their brightness and temperature, they discovered that most stars fell along a diagonal band on this diagram. This band became known as the main sequence, and stars on this sequence are in the prime of their lives. During this phase, which can last anywhere from a few million years for the most massive stars to trillions of years for the smallest, stars maintain a stable equilibrium between the outward pressure of fusion and the inward pull of gravity. Our Sun provides an excellent example of a main sequence star. It formed approximately 4.5 billion years ago from a collapsing cloud of gas and dust, possibly triggered by a nearby supernova explosion. Evidence for this comes from the presence of certain isotopes in our solar system that could only have been created in a supernova just before the Sun's formation. For the past 4.5 billion years, our Sun has been steadily converting hydrogen into helium in its core, and it will continue to do so for approximately another 5 billion years before exhausting its core hydrogen supply. During all this time, the Sun's output has been remarkably constant, varying by only a fraction of a percent. This stability has been crucial for the development of life on Earth. Even a modest increase or decrease in the Sun's energy output would dramatically affect Earth's climate and habitability. The main sequence represents a battle between two fundamental forces. Gravity constantly tries to compress the star, while the energy from fusion pushes outward. These forces remain in balance throughout the main sequence phase, but the balance isn't perfect. Stars gradually evolve even during this stable period. As helium accumulates in the core, replacing the hydrogen that has been fused, the core slowly contracts and heats up. This causes the rate of fusion to increase slightly, meaning that stars gradually brighten as they age. When our Sun first reached the main sequence, it was actually about 30% dimmer than it is today, and by the time it exhausts its core hydrogen, it will be significantly brighter than it currently is. This gradual brightening has implications for Earth's future. In perhaps another billion years, the Sun may have brightened enough to make Earth's surface too hot for liquid water, potentially ending the habitability of our planet long before the Sun actually leaves the main sequence. Not all stars are created equal, and astronomers have developed an elegant system for classifying them based on their most fundamental properties. The classification system astronomers use today was developed in the early 20th century, refined by scientists like Annie Jump Cannon, who classified hundreds of thousands of stars. This system categorizes stars primarily by their surface temperature, which manifests as color. The hottest stars appear blue or blue-white, while the coolest stars glow red. The classification uses letters that initially seem arbitrary: O, B, A, F, G, K, and M, from hottest to coolest. Generations of astronomy students have memorized these using the mnemonic, "Oh, be a fine girl, kiss me," though more modern variations have been created to be more inclusive. O-type stars are the behemoths of the stellar world, blazingly hot with surface temperatures exceeding 30,000 Kelvin. These blue giants are rare because they burn through their fuel so quickly, lasting only a few million years. Despite their scarcity, they dominate the appearance of regions where they exist because a single O-type star can outshine thousands of Sun-like stars. B-type stars are slightly cooler, but still intensely hot and luminous, with surface temperatures between 10,000 and 30,000 Kelvin. Many of the brightest stars in our night sky, including Rigel and Spica, belong to this class. A-type stars like Sirius and Vega have surface temperatures around 7,000 to 10,000 Kelvin and appear white to our eyes. These stars are still considerably more massive and luminous than our Sun. F-type stars represent a transition toward cooler, smaller stars, with temperatures of 6,000 to 7,000 Kelvin and a white to yellowish-white color. G-type stars include our Sun and have surface temperatures around 5,000 to 6,000 Kelvin, appearing yellow to our eyes. These stars are common throughout the galaxy and can maintain stable fusion for around 10 billion years, providing ample time for planets to form and life to potentially develop. K-type stars are cooler still, with temperatures of 3,500 to 5,000 Kelvin and an orange hue. These stars are becoming increasingly interesting to astronomers searching for habitable planets because they live even longer than G-type stars while still being luminous enough to warm planets in their habitable zones. Finally, M-type stars, the red dwarfs, are the coolest main sequence stars with surface temperatures below 3,500 Kelvin. These dim, red stars are by far the most common type of star in the galaxy, outnumbering all other types combined. Later additions to this classification system include L, T, and Y, classes for objects cooler than M-type stars, including brown dwarfs, which are objects too small to sustain hydrogen fusion and exist in a twilight zone between planets and stars. Each class is further subdivided into 10 numerical subclasses, from 0 to 9. So the Sun is specifically classified as a G2 star, indicating it falls near the hotter end of the G-type range. This classification system reveals that stars come in an enormous variety, from objects barely able to sustain fusion to blue supergiants hundreds of thousands of times more luminous than the Sun. Understanding where a star falls in this classification immediately tells astronomers much about its mass, age, and ultimate fate. To truly appreciate the nature of stars, it helps to examine one in detail. And fortunately, we have an excellent specimen close at hand. Our Sun might seem unique and special to us, but in cosmic terms, it's actually remarkably average. A middle-aged, medium-sized yellow dwarf star that wouldn't warrant a second glance from any cosmic surveyor. Yet understanding its properties provides crucial context for comprehending all stars. The Sun contains about 99.86% of all the mass in our solar system. Everything else, all the planets, moons, asteroids, comets, and dust, makes up barely more than 0.1%. In absolute terms, the Sun's mass is approximately 2 times 10 to the 30th power kilograms, or about 330,000 times the mass of Earth. To put this in perspective, you could fit over 1 million Earths inside the Sun's volume. The Sun's core, where fusion occurs, has a temperature of about 15 million Kelvin and a density over 150 times that of water, despite being gaseous. The immense pressure at the core, over 200 billion times Earth's atmospheric pressure, forces hydrogen nuclei to fuse into helium. This energy then takes a remarkable journey outward. Photons created in the core can take thousands or even hundreds of thousands of years to work their way to the surface because they're constantly absorbed and re-emitted by the dense stellar material. They undergo a random walk, bouncing around in the radiative zone before reaching the convective zone, where vast currents of plasma carry the energy toward the surface. When the energy finally reaches the surface, it escapes into space at the speed of light, taking just over 8 minutes to reach Earth. The Sun's surface, called the photosphere, has a temperature of about 5,700 Kelvin, giving it that characteristic yellow-white color. Above the photosphere lies the chromosphere, a thin layer visible during solar eclipses as a reddish glow. Beyond that extends the corona, the Sun's outer atmosphere, which paradoxically reaches temperatures exceeding 1,000,000 Kelvin, far hotter than the surface below. The mechanism heating the corona remains one of solar physics's enduring mysteries, though magnetic fields and plasma waves likely play crucial roles. The Sun rotates, but not as a solid body. Its equatorial regions complete a rotation in about 25 days, while regions near the poles take over 30 days. This differential rotation helps generate the Sun's complex magnetic field, which drives phenomena like sunspots, solar flares, and coronal mass ejections. At 4.6 billion years old, the Sun has completed about half its main sequence lifetime. It formed from a cloud of gas and dust enriched by previous generations of stars, giving it a composition of about 73% hydrogen, 25% helium, and 2% heavier elements, which astronomers collectively call metals, regardless of their chemical properties. This metallicity is important because it affects stellar evolution and the formation of planets. Compared to the oldest stars in the galaxy, which have almost no heavy elements, the Sun is relatively metal-rich, placing it in what astronomers call population 1 stars. In the context of the hundreds of billions of stars in the Milky Way, the Sun sits comfortably in the middle ranges of mass, size, temperature, and luminosity. Smaller, cooler red dwarfs vastly outnumber it, while larger, hotter stars are much rarer. This averageness has profound implications. It suggests that solar systems like ours might be quite common, and it means the Sun's evolution represents a typical pathway that countless other stars will follow. The stable equilibrium of the main sequence cannot last forever. Eventually, every star must exhaust the hydrogen fuel in its core. When this happens, the star's structure begins to change dramatically. For stars like the Sun, this transformation leads to a phase called the red giant stage, one of the most spectacular and violent periods in a star's life. As the hydrogen in the core depletes, fusion slows and eventually ceases. Without the outward pressure from fusion to counteract gravity, the core begins to contract. This contraction releases gravitational energy, heating the core and the surrounding shell of hydrogen that hasn't yet been fused. As this shell heats up, it eventually becomes hot enough to begin fusion itself. Now, the star is fusing hydrogen not in its core, but in a shell surrounding the core. This shell fusion releases even more energy than the core fusion did during the main sequence. But the energy distribution changes dramatically. The outer layers of the star absorb this energy and expand enormously. The Sun, when it becomes a red giant in about 5 billion years, will swell to perhaps 100 times its current diameter. Its outer layers will extend past the current orbit of Mercury and possibly Venus. Despite this massive increase in size, the surface cools as it expands, dropping to perhaps 3000 Kelvin. This cooler temperature gives the star its red color, hence the name red giant. Paradoxically, even though the surface is cooler, the star's total energy output increases dramatically because of its vastly increased surface area. A red giant can be hundreds or even thousands of times more luminous than it was on the main sequence. For any planets orbiting close to the star, the red giant phase spells doom. The intense radiation and expanding outer envelope will first bake these worlds, then potentially engulf them entirely. Earth's fate during the Sun's red giant phase remains uncertain. Some calculations suggest the Sun's outer layers will reach and consume the Earth. Others indicate that the Sun will lose so much mass during this phase that Earth's orbit will expand outward, potentially allowing it to escape being engulfed, though it will certainly be rendered uninhabitable. The Moon, Mars, and the outer planets will survive, but they will be transformed by the dramatically increased radiation from the bloated Sun. This phase is relatively brief in cosmic terms, lasting perhaps a few 100 million years for a Sun-like star, during which the star will pulse and vary in brightness as it struggles to maintain stability. Eventually, the helium accumulating in the core from hydrogen shell fusion becomes dense and hot enough to ignite its own fusion, combining helium into carbon and oxygen. For Sun-like stars, this helium ignition can be sudden and violent, an event called the helium flash, where the core fusion rate briefly spikes tremendously before settling into a stable rhythm. The star now fuses helium in its core and hydrogen in a surrounding shell, creating a complex layered structure. This helium-burning phase is briefer than the main sequence, lasting perhaps 100 million years for a solar mass star, because helium fusion produces less energy per unit mass than hydrogen fusion. When the core helium is exhausted, shell helium fusion begins, and the star may undergo further expansion into what's called the asymptotic giant branch, becoming even larger and more luminous. During these late stages, the star becomes unstable, pulsating and shedding mass in powerful stellar winds that blow the outer layers into space. The ultimate fate of stars like our Sun leads not to a violent explosion, but to a gradual fade-out, leaving behind an object of extraordinary density and strange properties. As the red giant star sheds its outer layers through stellar winds and pulsations, these gases form an expanding shell around the dying star. The hot core, now exposed, emits intense ultraviolet radiation that causes the expanding gas to fluoresce, creating what astronomers call a planetary nebula. This name is a historical artifact from when astronomers first observed these objects through primitive telescopes and thought they resembled planets. In reality, they have nothing to do with planets, but instead represent the beautiful death shroud of a sun-like star. These nebulae can take on extraordinary shapes, from simple spheres to complex butterfly or hourglass structures, depending on the star's magnetic field, rotation, and whether it had a binary companion. At the center of the planetary nebula lies the core itself, now called a white dwarf. This object represents the ultimate endpoint for any star born with less than about 8 times the Sun's mass, which includes the vast majority of stars in the universe. A white dwarf contains roughly the mass of the Sun compressed into a volume about the size of Earth. To comprehend this density, imagine taking 300,000 Earths and compressing them down to Earth's size. A teaspoon of white dwarf material would weigh several tons. The matter in a white dwarf exists in a state called electron degeneracy. The electrons are packed so tightly that quantum mechanical effects prevent them from being compressed further. This electron degeneracy pressure, arising from the Pauli exclusion principle, is what holds the white dwarf up against gravity. When first formed, a white dwarf can have a surface temperature of 100,000 Kelvin or more, making it intensely hot and bright despite its small size. The fierce ultraviolet radiation from this hot surface is what illuminates the surrounding planetary nebula. However, white dwarfs have no internal energy source. They don't undergo fusion. Instead, they simply radiate away their stored thermal energy into space. Over billions of years, a white dwarf cools and dims, fading through yellow, orange, and red before eventually becoming too dim to see. Theoretical calculations suggest that after trillions of years, a white dwarf will cool to the temperature of the cosmic microwave background, becoming a black dwarf. However, the universe is only about 13.8 billion years old, far too young for any white dwarf to have cooled completely. The oldest white dwarfs in the galaxy are around 10 billion years old and still glow faintly. White dwarfs come in several compositional types. Most are composed primarily of carbon and oxygen, the products of helium fusion. More massive progenitor stars can create white dwarfs, made of oxygen, neon, and magnesium, while less massive stars might leave behind helium white dwarfs. Though these require special circumstances to form and haven't had time to form through normal stellar evolution in the universe's current age. The maximum mass a white dwarf can have was calculated by Subrahmanyan Chandrasekhar and is about 1.4 times the Sun's mass. This Chandrasekhar limit exists because above this mass, electron degeneracy pressure can no longer support the star against gravity. If a white dwarf somehow gains mass beyond this limit, perhaps by accreting material from a companion star, it will be crushed by its own gravity, leading to either a neutron star or, more spectacularly, a Type I, a supernova that completely destroys the white dwarf. The universe contains examples that make our Sun look insignificant. While most stars are smaller and dimmer than our Sun, a select few are so enormous they defy comprehension. These are the supergiants and hypergiants, the true titans of the stellar realm. Supergiant stars can be dozens or even hundreds of times more massive than the Sun, and thousands of times more luminous. They represent the upper end of stellar mass, and their sheer scale staggers the imagination. Betelgeuse, the red supergiant marking Orion's shoulder, has a diameter estimated at around 700 times the Sun's diameter. If placed at the center of our solar system, Betelgeuse would engulf Mercury, Venus, Earth, and Mars, with its surface reaching partway to Jupiter's orbit. Yet even Betelgeuse is not the largest. That distinction currently belongs to stars like Ue Scuti or Stephenson 2-18, both red hypergiants whose exact sizes remain uncertain due to their diffuse outer atmospheres, but which may exceed 1,700 times the Sun's diameter. If you could somehow replace the Sun with one of these monsters, its outer surface would extend beyond Saturn's orbit. Flying an airplane around the equator of such a star at 500 miles per hour would take over 1,000 years to complete one circuit. The volume of these stars is almost inconceivable. You could fit over 5 billion suns inside the volume of the largest known stars. Despite their tremendous size, these giants are actually less dense than the air you're breathing right now. Their outer layers are so tenuous they constitute a near vacuum by Earth standards. Only in their cores, where gravity compresses matter to extraordinary densities and fusion occurs, does the material become dense. These stars are also profligate energy spenders. While the Sun converts about 600 million tons of hydrogen into helium every second, the most luminous stars convert millions of times more, radiating energy at rates up to 1,000,000 times the Sun's output. This prodigious energy generation comes at a cost. These stars live fast and die young. While the Sun will shine for 10 billion years, a supergiant might last only a few million years, and the most massive stars can exhaust their fuel in less than 1,000,000 years. The spectrum of these enormous stars reveals extreme conditions. Blue hypergiants like Eta Carinae have surface temperatures exceeding 25,000 Kelvin and lose mass through powerful stellar winds that blow off the star's outer layers at speeds of thousands of kilometers per second. Eta Carinae has ejected mass equivalent to several suns just in the past few centuries, creating the spectacular homunculus nebula that surrounds it. These winds are so powerful they can shape the space around the star, creating vast bubbles of hot gas and clearing out regions of the interstellar medium. When observed in detail, many of these extreme stars show evidence of violent instability, with brightness variations and outbursts suggesting they're barely holding themselves together. The outward pressure of their immense radiation almost balances their gravitational self-attraction, leaving them teetering on the edge of being torn apart by their own energy output. Red supergiants represent a different extreme. These stars, including Betelgeuse and Antares, have expanded to enormous sizes as they near the ends of their lives. Their cool surfaces, around 3,000 to 4,000 Kelvin, give them their distinctive red color. These stars pulse and vary in brightness as their outer layers expand and contract, sometimes changing their luminosity by factors of 2 or more over months or years. They're surrounded by shells and plumes of gas ejected during outbursts, visible in infrared observations. When these stars finally explode as supernovae, as Betelgeuse is expected to do within the next 100,000 years, they will briefly outshine their entire galaxy. The most luminous stars known, the hypergiants like R136A1 in the Large Magellanic Cloud, may have masses approaching 300 times the Sun's mass. Though even measuring such extreme objects challenges our instruments and theories. These stars exist at the absolute limit of what stellar physics allows. If stars were significantly more massive, the outward pressure from their radiation would overcome gravity and blow them apart. Indeed, the most massive stars constantly shed mass through fierce stellar winds, and some theories suggest there's a fundamental upper limit to stellar mass around 150 to 300 solar masses. Whatever the exact limit, these extreme stars demonstrate the incredible range of stellar properties and push our understanding of physics to its boundaries. The deaths of massive stars represent some of the most energetic events the universe has witnessed since the Big Bang itself. When a star much more massive than the Sun exhausts its nuclear fuel, it doesn't fade away gently like a sun-sized star. Instead, it destroys itself in a catastrophic explosion called a supernova that briefly rivals the brightness of an entire galaxy. The path to this violent end begins when the star has exhausted the hydrogen, then helium, then progressively heavier elements in its core. Unlike smaller stars, massive stars can fuse carbon into neon and magnesium, neon into oxygen and magnesium, oxygen into silicon and sulfur, and finally silicon into iron and nickel. Each successive stage burns hotter, faster, and releases less energy than the previous stage. The silicon burning phase lasts only about 1 day. When the core has been converted to iron, fusion must stop because iron is at the bottom of the binding energy curve. Fusing iron into heavier elements requires energy input rather than releasing energy, so it can't sustain the star. At this point, the star has an onion-like structure with layers of progressively lighter elements surrounding an iron core. The iron core grows as the silicon-burning shell continues to deposit iron into it. When the core's mass exceeds the Chandrasekhar limit of approximately 1.4 solar masses, electron degeneracy pressure can no longer support it against gravity. In a fraction of a second, the core collapses catastrophically. The collapse is faster and more violent than anything else in nature. The core implodes from the size of Earth to something only 30 kilometers across in less than a second. The matter falls inward at speeds approaching 1/4 the speed of light. As the core collapses, it becomes so dense that electrons are forced to combine with protons, creating neutrons and releasing neutrinos in a process called neutronization. When the collapsing core reaches nuclear density, the same density as an atomic nucleus, the collapse suddenly halts. The neutron degeneracy pressure stiffens the core, and the infalling material rebounds off this suddenly solid surface, creating a shockwave that propagates outward through the star. This shockwave carries colossal energy, equivalent to the Sun's total energy output over its entire 10 billion year lifetime, released in just a few seconds. The shockwave travels outward through the star's layers, heating them to billions of degrees and triggering explosive nuclear fusion that creates elements heavier than iron. These heavy elements, from copper and zinc to gold, uranium, and everything in between, are synthesized in the extreme conditions of the supernova explosion itself. When the shockwave reaches the surface of the star, it blows the outer layers into space at speeds of 10,000 to 30,000 kilometers per second, or up to 10% the speed of light. The explosion releases most of its energy, about 99%, in the form of neutrinos, ghostly particles that barely interact with matter and stream out from the collapsing core at nearly the speed of light. The visible explosion that we see is powered by the remaining 1% of the energy. Even this relatively small fraction is enough to make the supernova shine with the luminosity of billions of stars for weeks or months. At peak brightness, a supernova in a nearby galaxy can be visible to the naked eye, even across millions of light-years of space. The ejected material, traveling at tremendous speeds, slams into the surrounding interstellar medium, creating a supernova remnant that glows in radio waves, X-rays, and visible light. The Crab Nebula, remnant of a supernova observed by Chinese astronomers in 1054 CE, still glows brightly nearly 1,000 years later and continues to expand. These remnants can persist for tens of thousands of years before fading and mixing with the interstellar medium, enriching it with the heavy elements created in the star and its explosive death. Supernovae play a crucial role in galactic ecology. They inject energy into the interstellar medium, stirring it up and triggering new rounds of star formation when their shockwaves compress gas clouds. They distribute heavy elements throughout the galaxy, elements essential for forming rocky planets and life itself. Every atom in your body heavier than hydrogen was created either in the core of a star or in a supernova explosion. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in stellar furnaces and scattered by stellar explosions. In this very real sense, we are made of stardust, the products of stellar alchemy scattered across the cosmos. When the supernova's violence fades and the debris clears, something extraordinary may remain behind. If the collapsing core's mass falls within a certain range, roughly between 1.4 and 3 solar masses, the core's collapse is arrested by neutron degeneracy. Pressure, creating one of the strangest objects in the universe, a neutron star. These objects push matter to its absolute limits, creating conditions so extreme that they exist nowhere else except perhaps in the cores of colliding neutron stars, or in the first microseconds after the Big Bang. A neutron star packs more mass than the Sun into a sphere only about 20 kilometers in diameter, roughly the size of a city. The density is almost beyond comprehension. A sugar cube-sized chunk of neutron star material would weigh about 100 million tons, as much as all humanity combined. The matter in a neutron star is so compressed that atomic structure has completely broken down. Protons and electrons have been forced together to form neutrons, and these neutrons are packed together at nuclear density. In essence, a neutron star is a single atomic nucleus 20 kilometers across. The interior structure of neutron stars remains one of physics's great mysteries because we cannot replicate these conditions in any laboratory. The outer layer, or crust, consists of a lattice of atomic nuclei and free electrons. Below that lies a layer where neutrons begin to drip out of nuclei. Deeper still, free neutrons dominate, forming a superfluid that flows without friction. The core's properties are even more uncertain, with theories suggesting exotic forms of matter that may include strange quarks, pions, or other particles that exist nowhere else in the universe. Neutron stars have surface gravities about 200 billion times stronger than Earth's. If you could stand on a neutron star's surface, which you absolutely couldn't survive, you would weigh as much as a mountain weighs on Earth. Light itself is bent by the intense gravitational field, so much so that you might be able to see the back of your head as light curves around the star. The escape velocity from a neutron star's surface is approximately 1/3 the speed of light. Any object falling onto a neutron star would impact the surface with such energy that it would completely disintegrate, adding its mass to the neutron star and releasing a burst of X-rays. These objects also possess the strongest magnetic fields known in the universe. A typical neutron star has a magnetic field 1 trillion times stronger than Earth's, while a special class called magnetars can have fields 1,000 times stronger still, intense enough to be dangerous from thousands of kilometers away. Such fields can tear apart atoms, turning them into long chains aligned with the magnetic field lines. The magnetic field energy in a magnetar is so intense that the field actually affects the star's structure, twisting and deforming the crust, and occasionally causing starquakes when the crust suddenly cracks and settles into a new configuration. These starquakes can trigger tremendous explosions of X-rays and gamma rays that we can detect from across the galaxy. Neutron stars form with tremendous angular momentum inherited from their progenitor star's core. Because the core contracts from something the size of Earth to something only 20 kilometers across, conservation of angular momentum means neutron stars spin incredibly rapidly. Newly formed neutron stars can rotate hundreds of times per second, though they gradually slow down over millions of years as they lose rotational energy. The surface of a spinning neutron star moves at a substantial fraction of the speed of light. At these speeds, relativistic effects become important. Time actually runs slower at the surface compared to far from the star, and the star's shape distorts from a sphere to a slightly oblate form due to the centrifugal force. Perhaps the most remarkable property of neutron stars is that despite their extreme nature, we can observe them. They're far too small to see directly with any telescope, but they make themselves known through their emissions. Young neutron stars are extremely hot, with surface temperatures exceeding 1,000,000 Kelvin, and they emit X-rays as they cool. More spectacularly, many neutron stars announce their presence through regular pulses of radiation that sweep across space like a cosmic lighthouse beam. earning them the name pulsars. These remarkable objects were about to revolutionize our understanding of extreme physics. In 1967, graduate student Jocelyn Bell Burnell noticed something unusual in radio telescope data. A source in the sky was producing regular pulses of radio waves with a period of about 1.3 seconds, far more regular than any natural phenomenon then known. The regularity was so precise that the possibility of an artificial signal, perhaps from an extraterrestrial civilization, was seriously considered. The source was even jokingly designated LGM-1, for Little Green Men. When additional pulsing sources were discovered with different periods, the extraterrestrial hypothesis fell away, and astronomers realized they had discovered a new class of astronomical objects. These pulsars, as they came to be called, were soon identified as rapidly rotating neutron stars. The mechanism behind pulsars is surprisingly similar to a lighthouse. A neutron star has a powerful magnetic field that isn't aligned with its rotation axis. Charged particles near the star's surface are accelerated along the magnetic field lines, and as they accelerate, they emit radiation, particularly radio waves. This radiation beams out along the magnetic poles. As the neutron star rotates, these beams sweep through space like a lighthouse beam. If Earth happens to lie in the path of one of these beams, we see a pulse of radiation each time the beam sweeps past us. The pulses are extraordinarily regular because neutron stars are such precise rotators, their rotation disturbed by very little in the vacuum of space. The fastest pulsars are truly astonishing. Millisecond pulsars can spin hundreds of times per second, with the current record holder rotating at over 700 times per second. These incredibly rapid rotators are thought to be old neutron stars that have been spun up by accreting matter from a companion star, a process that transfers angular momentum to the neutron star. The matter spirals onto the neutron star in an accretion disk, and as it falls into the intense gravitational field, it speeds up the neutron star's rotation. When the accretion eventually stops, the neutron star is left spinning at these incredible rates. At 700 rotations per second, the surface of the neutron star is moving at about 1/10 the speed of light. Pulsar timing is so precise that astronomers can use them as cosmic clocks. The most stable pulsars rival atomic clocks in their precision, with pulse arrival times predictable to within microseconds over years. This precision has allowed astronomers to detect subtle effects like the influence of gravitational waves passing through space, which slightly change the arrival. Times of pulsar signals. Arrays of pulsars spread across the sky are being used as a galaxy-spanning gravitational wave detector, sensitive to waves with periods of years caused by supermassive black holes orbiting each other in distant galaxies. This technique represents one of the most innovative uses of neutron stars as cosmic laboratories. Some pulsars have revealed themselves to have planets, detected through tiny variations in the pulse timing caused by the gravitational pull of our orbiting worlds. These pulsar planets are thought to be either remnants of planets that survived the supernova explosion, or new worlds formed from the debris disk around the neutron star after the explosion. Either scenario presents a hellish environment for any world, bathed in intense radiation from the pulsar's beams and magnetic field. These discoveries were historically significant because they represented the first confirmed detection of planets outside our solar system, discovered even before the first planets around normal stars were found. Pulsars also come in different varieties based on their emission characteristics. Radio pulsars emit primarily in radio wavelengths. X-ray pulsars emit X-rays, often powered by accretion from a companion star, with the accreting material funneled onto the magnetic poles where it impacts the surface and creates hotspots that emit X-rays. Magnetars, those neutron stars with the most extreme magnetic fields, occasionally produce bursts of gamma rays and X-rays when their crusts crack in starquakes, releasing magnetic energy equivalent to the Sun's total output over thousands of years in just a fraction of a second. Some pulsars have been observed to suddenly change their rotation rate in events called glitches, where the rotation speeds up abruptly, likely due to interactions between the superfluid interior and the crust. The study of pulsars has provided crucial tests of physics in extreme conditions. The orbital decay of a binary pulsar system, where two neutron stars orbit each other, provided the first indirect evidence for gravitational waves, exactly matching Einstein's predictions from general relativity. This discovery earned the Nobel Prize in Physics in 1993. More recently, the direct detection of gravitational waves from merging neutron stars in 2017 opened an entirely new way to study these objects, revealing that neutron star collisions are likely the primary source of heavy elements like gold and platinum in the universe. As neutron stars spiral together and merge, they create conditions even more extreme than supernova explosions, synthesizing the heaviest elements through rapid neutron capture processes. Yet for all their extremity, neutron stars are not the final word in stellar remnants. If a stellar core is too massive even for neutron degeneracy pressure to support, if it exceeds approximately 3 solar masses when it collapses, then nothing can stop the collapse. No known force in physics can prevent what happens next. The core continues collapsing past the neutron star stage, past any conceivable density, until it forms something that Einstein's equations predict, but that defies intuition: a black hole. This represents the ultimate endpoint for the most massive stars, a point where matter becomes so compressed that it creates a rupture in the fabric of space-time itself. Black holes are not objects in the traditional sense. They are regions of space-time where gravity has become so intense that it warps space and time beyond recognition. At the center of a black hole, all the mass collapses to a point of infinite density called a singularity, where our current theories of physics break down. Surrounding the singularity is the event horizon, a spherical boundary from which nothing, not matter, not light, not information of any kind, can escape. The radius of the event horizon, called the Schwarzschild radius, depends only on the black hole's mass. For a stellar mass black hole of about 10 solar masses, the event horizon has a radius of about 30 kilometers. Despite containing more mass than 10 suns, the black hole's event horizon would fit comfortably inside a medium-sized city. The properties of black holes challenge our everyday understanding of reality. Time itself behaves strangely near a black hole. As you approach the event horizon, time as measured by a distant observer slows down. An observer watching someone fall toward a black hole would see them slow down and eventually appear to freeze at the event horizon, with their image becoming increasingly redshifted and dimmer but never quite crossing the boundary. However, from the perspective of the falling person, nothing special happens at the event horizon. They would cross it in finite time by their own clock, though they would not survive long afterward. The tidal forces near a black hole, the difference in gravitational pull between your head and feet, would stretch any object into a thin stream in a process gruesomely called spaghettification. Despite their name, black holes are not cosmic vacuum cleaners that suck in everything around them. Far from a black hole, its gravitational pull is no different than any other object of the same mass. If the Sun were suddenly replaced by a black hole of the same mass, Earth's orbit would remain unchanged. though we would quickly freeze in the darkness. The danger from black holes comes only when you get very close to them, within a few times the Schwarzschild radius. At these distances, the gravitational field becomes so strong and changes so rapidly with distance that the tidal forces become destructive. Black holes can be detected despite not emitting light themselves. Material falling toward a black hole forms an accretion disk, a swirling disk of gas and dust that heats up through friction and gravitational compression. The inner regions of the accretion disk, spiraling just outside the event horizon, reach temperatures of millions of degrees and emit intense X-rays. These X-ray emissions can be detected from Earth, allowing astronomers to identify black hole candidates. The material in the accretion disk doesn't fall straight in, but instead spirals inward, gradually losing angular momentum through friction and magnetic interactions. As it spirals closer to the event horizon, it orbits faster and faster, reaching significant fractions of the speed of light in the innermost stable orbit just outside the event horizon. Some black holes produce spectacular jets of material perpendicular to the accretion disk. These jets, powered by processes involving the black hole's rotation and magnetic fields threading the accretion disk, can extend for thousands of light years into space, traveling at speeds very close to the speed of light. The exact mechanism generating these jets remains an active area of research, but they rank among the most powerful sustained energy releases in the universe. Stellar mass black holes can produce jets, but they pale in comparison to the jets from supermassive black holes in the centers of galaxies, which can be powerful enough to affect the evolution of their entire host galaxy. Recent advances have allowed astronomers to detect black holes through gravitational waves. When two black holes orbit each other, they emit gravitational waves that carry away energy, causing the orbit to decay. As they spiral closer together, the orbital period decreases and the gravitational wave frequency increases, creating a characteristic chirp signal. When the black holes finally merge, they create a single, larger black hole, releasing enormous amounts of energy as gravitational waves. The LIGO and Virgo detectors have observed dozens of these mergers, revealing a population of stellar mass black holes more massive than theorists expected, with some exceeding 50 solar masses. These observations have revolutionized our understanding of stellar evolution and the formation of black holes. The Event Horizon Telescope, a planet-sized array of radio telescopes working together, has even captured images of the shadows of supermassive black holes, showing the photon ring where light bends around the black hole's event horizon. While these are not stellar mass black holes, but rather the supermassive monsters in galactic centers, the achievement demonstrates that black holes, despite their nature as regions from which light cannot escape, can be observed and studied through their effects on surrounding matter and light. The study of black holes continues to push the boundaries of physics, testing general relativity in its most extreme regime, and potentially offering clues about how to unite gravity with quantum mechanics in a theory of quantum gravity. Throughout our exploration of stellar death and exotic remnants, we've assumed stars exist in isolation, but this assumption is incorrect for most stars in the galaxy. The majority of stars, perhaps as many as 70%, exist in binary or multiple star systems where two or more stars orbit their common center of mass. These systems exhibit behaviors and phenomena impossible for solitary stars, and their interactions can dramatically alter stellar evolution, sometimes leading to spectacular cosmic fireworks. The formation of multiple star systems occurs during the initial collapse of a molecular cloud. If the cloud has sufficient angular momentum or fragments during collapse. Multiple cores can form, creating a system of 2 or more protostars that are gravitationally bound to each other. Binary star systems come in many configurations. In wide binaries, the stars may be separated by hundreds or thousands of astronomical units, taking centuries or millennia to complete one orbit. These stars evolve largely independently, each following the path a solitary star would take. Close binaries, where the stars orbit within just a few stellar radii of each other, present a far more interesting situation. In these systems, the gravitational influence of each star distorts the shape of its companion, and material can flow from one star to the other, dramatically affecting both stars' evolution. The closest binaries can have orbital periods of just hours, with the stars' surfaces nearly touching as they whirl around each other at tremendous speeds. The Roche lobe defines the region around each star where that star's gravity dominates. If a star expands beyond its Roche lobe, material can spill over onto its companion in a process called mass transfer. This typically happens when one star evolves into a red giant and swells up. The transferred material doesn't fall directly onto the companion, but instead forms an accretion disk around it due to angular momentum conservation. The accretion disk becomes heated by friction and viscous forces, glowing brightly and sometimes outshining the stars themselves. As material spirals inward through the accretion disk, it eventually reaches the surface of the accreting star, releasing gravitational potential energy that can heat the system to millions of degrees. If the accreting star is a white dwarf, the consequences can be dramatic. Hydrogen from the donor star accumulates on the white dwarf's surface, where the intense gravity compresses it. Eventually, enough hydrogen accumulates that the pressure and temperature at the base of this layer becomes sufficient to ignite fusion. However, unlike fusion in normal stars, which has a self-regulating feedback mechanism, the degenerate matter of the white dwarf doesn't respond normally to heating. When fusion ignites, it runs away explosively, consuming all the accumulated hydrogen in a thermonuclear explosion called a nova. The explosion doesn't destroy the white dwarf, but instead blows off the accreted layer, brightening the system by factors of thousands or millions and making it visible to the naked eye for a few weeks before it fades back to obscurity. This process can repeat, with the white dwarf gradually accumulating more material from its companion, leading to another nova explosion years or decades later. These recurrent novae demonstrate that mass transfer in binary systems is ongoing over long periods. Even more spectacularly, if the white dwarf accumulates enough mass to push it over the Chandrasekhar limit, the entire white dwarf undergoes a catastrophic collapse, followed by a complete thermonuclear explosion called a Type Ia supernova. These supernovae are incredibly important for cosmology because they have remarkably consistent peak brightnesses, making them excellent standard candles for measuring cosmic distances. Observations of distant Type Ia supernovae provided the first evidence that the universe's expansion is accelerating, leading to the discovery of dark energy. Binary systems containing neutron stars or black holes exhibit even more extreme behavior. Material accreting onto a neutron star can heat up to billions of degrees, emitting copious X-rays and making these X-ray binaries some of the brightest X-ray sources in the sky. The infalling matter can also spin up the neutron star, potentially creating millisecond pulsars. Some X-ray binaries are transient, alternating between quiet states and outburst states when material suddenly floods onto the compact object. The physical processes governing these outbursts involve instabilities in the accretion disk and remain subjects of active research. When two neutron stars orbit each other, They emit gravitational waves that carry away energy, causing the orbit to gradually decay. Eventually, after millions or billions of years, the neutron stars spiral together and merge in a violent collision that produces gravitational waves, gamma-ray bursts, and creates heavy elements through rapid neutron capture. Eclipsing binary systems provide another fascinating phenomenon. When the orbital plane of a binary system aligns with our line of sight, the stars periodically pass in front of each other as seen from Earth, causing the system's brightness to drop during each eclipse. These eclipsing binaries have been invaluable for astronomy because careful analysis of the light curves, the patterns of brightness variations, reveals detailed information about the stars' sizes, masses, temperatures, and orbital parameters. The transiting exoplanet detection method, which has discovered thousands of planets around other stars, is essentially the same technique applied to planet-star systems instead of binary stars. Some binary systems are so close and massive that they're expected to merge entirely. When two massive stars in a tight binary exhaust their fuel and collapse, they might not form a traditional binary of compact objects, but instead merge during their death throes. These merger events may explain some of the most luminous supernovae observed, called superluminous supernovae, which exceed the brightness of typical supernovae by factors of 10 to 100. The exact mechanisms remain uncertain, but the interaction between two dying massive stars can release tremendous amounts of energy and create exotic outcomes. Triple and quadruple star systems add additional complexity, with hierarchical orbits where inner pairs orbit each other while also orbiting a common center with outer companions. These complex gravitational dances can lead to instabilities and even ejections, where one star gains enough energy to be flung out of the system entirely. While binary interactions can be dramatic, some stars change in brightness without any companion star involvement. These variable stars exhibit intrinsic variations in luminosity due to physical processes within the stars themselves. Variable stars come in numerous types, each with different causes for their variability, and many have played crucial roles in astronomical discoveries. Understanding variable stars requires understanding stellar structure and the various instabilities that can develop in stars under different conditions. Some variability is regular and predictable, while other types are irregular or eruptive, making each class of variable star unique in its behavior and importance. Pulsating variable stars physically expand and contract, changing in size, temperature, and brightness as they oscillate. These pulsations arise from instabilities in the star's structure, often driven by partial ionization zones, where helium transitions between different ionization states. As the star contracts, these zones heat up and become more opaque, trapping radiation. The trapped radiation pressure causes the outer layers to expand. As they expand, they cool and become more transparent, releasing the trapped radiation and causing them to contract again, starting the cycle anew. This kappa mechanism, as it's called, drives pulsations in many types of variable stars. Cepheid variables are among the most famous pulsating variables. These are supergiant stars that pulsate with periods ranging from about 1 day to over 100 days, with longer period Cepheids being more luminous. The American astronomer Henrietta Swan Leavitt discovered in the early 20th century that Cepheids follow a period luminosity relationship. By measuring a Cepheid's pulsation period, you can determine its intrinsic luminosity. Comparing this intrinsic luminosity with its apparent brightness then reveals its distance. This discovery transformed astronomy, providing the first reliable method for measuring distances to nearby galaxies. Cepheid variables in the Andromeda galaxy allowed Edwin Hubble to prove that Andromeda was indeed a separate galaxy far beyond the Milky Way, forever changing our understanding of the universe's scale. RR Lyrae variables are another important class of pulsating stars. These are older, lower mass stars than Cepheids, typically found in globular clusters. They pulsate with periods less than 1 day, and all have roughly the same intrinsic luminosity, making them excellent standard candles for measuring distances to globular clusters and the Milky Way's halo. By determining the distances to globular clusters using RR Lyrae stars, astronomers have mapped the three-dimensional structure of the Milky Way's halo and determined distances to nearby galaxies that have been resolved into individual stars. Mira variables are long-period pulsating red giants that vary in brightness by factors of hundreds over periods of months to years. The star Mira itself, the first variable star discovered and recognized as truly variable, changes from second or third magnitude at maximum to below naked eye visibility at minimum over a period of about 330 days. These dramatic pulsations occur in stars on the asymptotic giant branch, near the ends of their lives. The pulsations are so violent that they help drive mass loss through stellar winds, with the star shedding its outer layers into space. This mass loss creates beautiful shells of gas around Mira variables visible in infrared and ultraviolet observations. Delta Scuti variables are shorter period pulsators, typically main sequence or slightly evolved stars that pulsate with periods of a few hours. Multiple pulsation modes can be excited simultaneously in these stars, creating complex light curves with multiple periodicities superimposed. Analyzing these multiple frequencies through asteroseismology allows astronomers to probe the internal structure of these stars, much like seismologists use earthquake waves to study Earth's interior. The field of asteroseismology has exploded in recent years with high-precision photometry from space telescopes, revealing that the Sun and many other stars exhibit numerous low-amplitude pulsation modes that provide detailed information about stellar interiors. Not all variable stars pulsate regularly. Eruptive variables show sudden increases in brightness due to violent processes in or on the star. T Tauri stars are young, pre-main sequence stars that vary irregularly as they undergo the final stages of contraction toward the main sequence. Their variability stems from instabilities in their accretion disks, changes in circumstellar extinction as dust clouds pass in front of them, and magnetic activity including stellar flares far more powerful than solar flares. Flare stars, typically red dwarfs, can suddenly brighten by several magnitudes in minutes due to tremendous magnetic reconnection events in their atmospheres that release energy equivalent to millions of hydrogen bombs. Cataclysmic variables include novae and related systems, where a white dwarf accretes material from a companion, showing outbursts ranging from subtle dwarf novae eruptions every few weeks to classical novae that brighten by millions of times over a few days. Symbiotic stars combine a red giant with a hot white dwarf, showing complex variability as the white dwarf ionizes the red giant's stellar wind, creating emission nebulae around the binary system. Each class of variable star provides unique insights into stellar physics, from the internal structure of pulsating stars to the violent interactions in accreting binaries to the magnetic dynamos powering stellar flares. The diversity of variable stars reflects the enormous range of physical conditions and evolutionary states found among stars. By studying their variations, astronomers probe stellar interiors, map stellar atmospheres, measure cosmic distances, and observe the violent interactions that govern stellar evolution in binary systems. Variable stars have contributed to nearly every major discovery in 20th century astronomy, from the scale of the universe to the nature of stellar death, demonstrating that sometimes the most revealing objects are those that change rather than those that remain constant. All the diversity we've discussed, from the smallest red dwarfs to the largest hypergiants, from main sequence stability to explosive death, stems from one fundamental process: nuclear fusion. The forging of elements in stellar cores and explosive events represents one of the most profound connections between the microscopic quantum world and the cosmic scale of astronomy. Every element heavier than hydrogen owes its existence to stellar nucleosynthesis, the suite of nuclear reactions that transmute lighter elements into heavier ones. Understanding how stars create elements reveals not only the inner workings of stars, but also explains the chemical composition of everything around us, from planets to people. The story begins with the Big Bang, which created mostly hydrogen and helium, with trace amounts of lithium and beryllium. These primordial elements emerged from the first few minutes of the universe, when conditions were hot and dense enough for nuclear reactions, but not so extreme that all matter remained as fundamental particles. As the universe expanded and cooled, it was left with a composition of roughly 75% hydrogen and 25% helium by mass, along with infinitesimal amounts of heavier elements. This primordial composition persists in the oldest stars, formed before stellar nucleosynthesis had significantly enriched the interstellar medium with heavier elements. Every other element, every carbon atom in every living thing, every oxygen molecule you breathe, every iron atom in your blood, was created later in stars. The first step in stellar nucleosynthesis is the fusion of hydrogen into helium through the proton-proton chain, or the CNO cycle, depending on the star's temperature. In stars like the Sun, the proton-proton chain dominates. This process begins when two protons collide with sufficient energy to overcome their electromagnetic repulsion and fuse via the weak nuclear force, converting one proton to a neutron and creating deuterium, a heavy hydrogen isotope. The deuterium quickly fuses with another proton to form helium-3, and two helium-3 nuclei can then combine to form helium-4 plus 2 protons. This complex chain of reactions happens countless times every second in the Sun's core, gradually converting hydrogen to helium and releasing energy that keeps the Sun shining. In more massive stars with hotter cores, the CNO cycle becomes more important. This cycle uses carbon, nitrogen, and oxygen as catalysts. Protons are added successively to carbon-12, transforming it through nitrogen 13, nitrogen-14, and oxygen-15, before a final reaction converts it back to carbon-12 while producing a helium-4 nucleus. The CNO cycle is temperature sensitive, so massive stars generate most of their energy through this process, while cooler stars like the Sun rely primarily on the proton-proton chain. Regardless of the pathway, the net result is the same. 4 hydrogen nuclei become one helium nucleus, releasing energy because helium-4 is slightly less massive than 4 hydrogen nuclei, with the missing mass converted to energy according to Einstein's famous equation. When a star exhausts the hydrogen in its core, more massive stars can proceed to helium fusion. At temperatures around 100 million Kelvin, helium nuclei can overcome their mutual repulsion and fuse. The triple alpha process combines 3 helium-4 nuclei to form carbon-12. This reaction must occur in 2 steps. First, 2 helium nuclei form unstable beryllium-8, which normally decays back to 2 helium nuclei almost immediately. However, At the high densities in stellar cores, there's a chance that a third helium nucleus collides with the beryllium-8 before it decays, forming carbon-12. This process critically depends on a resonance in the carbon-12 nucleus that enhances the reaction rate. If this resonance didn't exist with precisely the energy it has, carbon would be extremely rare in the universe, and carbon-based life would be impossible. Once carbon exists in the core, additional helium can fuse with it to create oxygen-16, and then potentially neon-20, magnesium-24, and so forth, each time adding one helium nucleus. In the most massive stars, after helium is exhausted, carbon fusion can begin at temperatures around 600 million Kelvin. Carbon nuclei fuse to create neon, sodium, and magnesium. Following carbon burning comes neon burning around 1 billion Kelvin, then oxygen burning around 2 billion Kelvin, and finally silicon burning at over 3 billion Kelvin. Each successive stage occurs at higher temperatures, burns faster, and releases less energy per unit mass than the previous stage. Silicon burning doesn't actually fuse silicon nuclei together directly. Instead, at these extreme temperatures, photons are energetic enough to break apart silicon nuclei, creating a mix of lighter nuclei that rapidly recombine in various ways. The end result is that silicon is gradually converted to iron group elements like iron, nickel, and cobalt. This process creates the onion layer structure in massive stars, with iron in the core surrounded by shells burning silicon, oxygen, neon, carbon, helium, and hydrogen. Each shell exists in a delicate equilibrium, burning its fuel and depositing ash that will be incorporated into the next shell wood. Iron represents the end of the line for fusion as an energy source. Iron 56 is the most tightly bound nucleus, meaning it has the lowest mass per nuclear particle. Fusing iron into heavier elements requires energy input rather than releasing energy, so iron cannot fuel the star. This is why massive stars develop iron cores that eventually collapse, leading to supernovae. The supernova explosion itself creates conditions extreme enough to forge elements heavier than iron. In the collapsing core and the expanding shockwave, neutrons become abundant, and rapid neutron capture, called the R process, builds up heavy elements up to and beyond uranium by adding neutrons faster than they can radioactively decay. There's also a slow neutron capture process, the S process, that occurs in the helium-burning shells of red giants. Here, neutrons are produced at lower rates, allowing unstable isotopes to beta decay before capturing another neutron. This creates a different pattern of heavy element abundances than the R process. The combination of these processes, along with other mechanisms like proton capture and photodisintegration in various stellar environments, creates the full periodic table of elements. Recent observations of neutron star mergers have confirmed that these collisions produce tremendous amounts of heavy elements through R-process nucleosynthesis, solving a long-standing mystery about where the heaviest elements originate. The profound implication is that we are literally made of stardust. The hydrogen in water molecules was created in the Big Bang, but the oxygen came from massive stars that exploded before the sun formed. The carbon in every organic molecule was forged in the cores of red giants. The calcium in your bones, the iron in your hemoglobin, the phosphorus in your DNA, all were created in stellar furnaces and scattered into space by stellar winds and supernova explosions. The gold in jewelry requires even more extreme conditions, likely created when neutron stars collided billions of years ago. When you look at the night sky, you're not just seeing distant suns. You're seeing the cosmic forges that created the very atoms that make up your body. the factories that made existence as we know it possible. Determining how far away stars are presents one of the most fundamental challenges in astronomy. Without knowing distance, we cannot determine a star's true luminosity, size, or many other critical properties. For millennia, stars appeared as points of light with no indication of their distances. Even the nearest stars are so far away that measuring their distances requires careful technique and clever methods. The history of measuring stellar distances is a history of expanding our cosmic horizons, pushing back the boundaries of the known universe step by careful step. Each new technique extends our reach, but also introduces new uncertainties and limitations. The most direct method for measuring stellar distances is parallax, the same principle that causes nearby objects to appear to shift position when you view them from different locations. As Earth orbits the Sun, our viewing position changes by about 300 million kilometers over 6 months. This baseline is large enough that the nearest stars appear to shift slightly against the background of more distant stars. The size of this shift, measured in fractions of an arcsecond, reveals the star's distance through simple trigonometry. An arcsecond is 1/36th of a degree, already incredibly small, and the parallax shifts of even nearby stars are smaller still. The nearest star system, Alpha Centauri, has a parallax of about 3/4 of an arcsecond. This defines the parsec, the primary distance unit in astronomy. 1 parsec is the distance at which a star would have a parallax of 1 arcsecond, equal to about 3.26 light years or 30 trillion kilometers. Most stars are much farther away, with correspondingly smaller. Parallaxes. Ground-based telescopes could measure parallaxes down to about 0.01 arcseconds, reaching stars up to 100 parsecs away, but atmospheric turbulence limited accuracy. The European Space Agency's Hipparcos satellite, launched in 1989, measured parallaxes for over 100,000 stars with much greater precision, and its successor Gaia is currently measuring parallaxes for over 1 billion stars with micro-arcsecond precision, revolutionizing our three-dimensional map of the nearby galaxy. Beyond the reach of parallax measurements, astronomers must use indirect methods based on the intrinsic properties of stars. Standard candles, objects with known intrinsic luminosity, allow distance determination by comparing their known luminosity with their observed brightness. The inverse square law tells us that brightness decreases with the square of distance. So if we know an object's true luminosity and measure its apparent brightness, we can calculate its distance. Cepheid variables provide excellent standard candles because of the period luminosity relationship discovered by Henrietta Swan Leavitt. Measuring a Cepheid's pulsation period reveals its luminosity, and comparing this with its observed brightness gives its distance. Type Ia supernovae serve as standard candles for even greater distances because they're so bright they can be seen across billions of light years. These supernovae have remarkably consistent peak brightnesses because they all result from white dwarfs exploding when they reach the Chandrasekhar limit, undergoing essentially the same physical process. Small variations in peak brightness correlate with the supernova's light curve shape, allowing astronomers to standardize them further. Observations of distant type Ia supernovae provided the first evidence that the universe's expansion is accelerating, one of the most important discoveries in modern cosmology. Other distance indicators include RR Lyrae variables, the Tully-Fisher relation that links a galaxy's rotation speed to its luminosity, and even the existence of hot, massive stars which can only exist relatively nearby given their short lifetimes. Astronomers have constructed what's called the cosmic distance ladder, a series of overlapping techniques that each extend beyond the previous method's reach. parallax reaches to perhaps 10,000 light-years with current technology. Cepheids extend to about 100 million light-years. Type Ia supernovae reach to billions of light-years, allowing measurement of distances across a significant fraction of the observable universe. Each rung of this ladder depends on calibrating the previous rung, so uncertainties compound. If our parallax measurements are off, that error propagates through Cepheid distances to supernova distances. This has led to significant effort to precisely calibrate each step. The distance scale also reveals the universe's expansion rate, the Hubble constant, which describes how fast distant galaxies are receding due to cosmic expansion. Current measurements show some tension between different methods, with some suggesting a faster expansion than others, a discrepancy that may hint at new physics, or may simply reflect remaining systematic uncertainties in the distance measurements. For the most distant objects, we can only estimate distances based on redshift, the stretching of light due to the expansion of space itself. The relationship between redshift and distance depends on cosmological parameters, including the amounts of dark matter and dark energy in the universe, introducing additional complexity. Despite these challenges, the measurement of cosmic distances stands as one of astronomy's great achievements, allowing us to map the universe from our backyard to the edges of the observable cosmos, revealing a universe billions of light-years across, containing billions of galaxies, each with billions of stars. Stars rarely exist in true isolation. They form in groups, born together from the same molecular cloud, sharing common origins and often remaining gravitationally bound for millions or billions of years. These stellar associations and clusters provide natural laboratories for studying stellar evolution because all the stars in a cluster formed at essentially the same time from material with the same composition. The only variable is mass, allowing astronomers to observe how stars of different masses evolve. Clusters come in two basic types with very different properties, origins, and ages: open clusters and globular clusters, each revealing different aspects of our galaxy's history and structure. Open clusters, also called galactic clusters, are relatively loose associations of hundreds to thousands of stars spanning regions 10 to 30 light-years across. These clusters form in the spiral arms of galaxies from giant molecular clouds. The stars are relatively young, ranging from just formed to about a few billion years old, with most open clusters being far younger than this. Many open clusters are still associated with the nebula from which they formed, their bright young stars illuminating the remaining gas and dust. The Pleiades, easily visible to the naked eye as a compact group of bright stars in the constellation Taurus, represents a classic open cluster about 100 million years old, still containing the hot blue stars that formed when dinosaurs walked the Earth. Open clusters are not tightly bound by gravity. The star's individual velocities are comparable to the cluster's escape velocity, meaning stars gradually drift away, and external gravitational influences from the galaxy disrupt the cluster over time. Most open clusters dissolve within a few hundred million years as their member stars slowly disperse into the galactic disk. However, while they exist, they provide excellent test cases for stellar evolution models. By observing which stars have left the main sequence and which remain, astronomers can determine the cluster's age because more massive stars evolve faster. The Hertzsprung-Russell diagram of an open cluster shows a main sequence truncated at some mass, with more evolved stars having moved to the red giant branch. The location of this turn-off point reveals the cluster's age. Thousands of open clusters are known in the Milky Way, though the actual number must be far higher, with many hidden behind dust, or too dispersed to easily recognize. The Sun likely formed in an open cluster about 4.5 billion years ago, though its sibling stars have long since dispersed throughout the galaxy. By analyzing the chemical compositions of stars throughout the Milky Way, astronomers have attempted to find the Sun's lost siblings, stars born from the same molecular cloud, though this proves extraordinarily difficult after billions of years of orbital evolution. Globular clusters present a stark contrast. These are ancient, densely packed spheres of stars containing tens of thousands to millions of members within regions only 50 to 100 light-years across. The stars are packed so densely in the cluster's core that they are separated by distances of only light weeks or even light days. Compared to the light years between stars in the Sun's neighborhood, if Earth orbited a star in a globular cluster's core, the night sky would contain hundreds or thousands of stars brighter than Sirius, the brightest star in our sky. This stellar density leads to frequent gravitational interactions, with stars occasionally passing close enough to disrupt binary systems or even collide, creating exotic objects like blue stragglers, stars that appear younger than they should because they've gained fresh fuel through collisions or mergers. Globular clusters are ancient, typically 10 to 13 billion years old, nearly as old as the universe itself. They formed in the early Milky Way, likely during the galaxy's initial collapse, and they orbit in the galactic halo rather than the disk, following orbits that can take them far above and below the galactic plane. The Milky Way has about 150 to 160 known globular clusters, distributed in a roughly spherical halo centered on the galactic core. Other large galaxies have similar systems of globular clusters, with giant elliptical galaxies sometimes hosting thousands of them. The stars in globular clusters are population 2 stars, metal poor compared to stars like the Sun, because they formed before many generations of stellar nucleosynthesis had enriched the interstellar medium. This low metallicity affects their properties and evolution, making them appear slightly different from younger, metal-rich stars of the same mass. All the massive stars in globular clusters have long since evolved and died. The remaining stars are lower mass than the Sun, slowly burning their hydrogen on the main sequence or evolved into red giants. The most massive stars remaining on the main sequence in ancient globular clusters are only slightly less massive than the Sun, which tells us these clusters must be extremely old since these stars take 10 billion years or more to exhaust their core hydrogen. Globular clusters have provided crucial insights into stellar evolution, galactic structure, and cosmology. The distances to globular clusters, determined using R.R. Lyrae variables, helped map the Milky Way's size and structure. Observing the main sequence turn off in globular clusters provides age estimates for the oldest stars in the galaxy, constraining the age of the universe itself. The existence of multiple stellar populations within individual globular clusters, with subtle chemical differences, has revealed that globular clusters had more complex formation histories than previously thought, possibly forming in multiple bursts or accreting gas between generations of star formation. Some astronomers even speculate that globular clusters might be the stripped cores of dwarf galaxies that merged with the Milky Way billions of years ago, with the clusters representing all that remains of these ancient galaxies. Within any cluster, young or old, the diversity of stellar ages and masses tells a story of cosmic evolution. The oldest stars are time capsules, preserving information about the early universe, while the younger stars represent ongoing stellar birth that continues to this day. Understanding the age distribution of stars throughout the galaxy reveals its history, from its violent formation through billions of years of gradual evolution to its present state, the chemical compositions of stars of different ages track how the galaxy has been enriched with heavy elements over time, connecting stellar evolution to galactic evolution in an intricate cosmic cycle. The oldest stars in the galaxy are found predominantly in the halo and in globular clusters. These ancient objects formed within the first billion years after the Big Bang, when the universe was still relatively young and contained almost no elements heavier than helium. Astronomers classify stars by their metallicity, using the term metals to refer to all elements heavier than helium, regardless of their chemical properties. Population 3 stars, the very first generation of stars that formed from completely pristine primordial gas containing only hydrogen and helium, have never been directly observed. These hypothetical objects would have been massive, perhaps hundreds of solar masses, burning through their fuel quickly and exploding as supernovae. After only a few million years, their explosions would have enriched the surrounding gas with the first heavy elements, seeding the formation of subsequent generations. Population 2 stars, including those in globular clusters and the galactic halo, formed from gas that had been slightly enriched by population 3 supernovae. These stars have metallicities as low as 1/10,000th of the Sun's metallicity. The existence of any heavy elements at all in these stars proves they must have formed after at least one generation of massive stars lived and died. The most metal-poor stars known have iron abundances less than 100,000th that of the Sun, making them among the most pristine objects we can observe. These ultra-metal-poor stars serve as fossil records of the early universe, preserving in their atmospheres the chemical signatures of the very first supernova. By analyzing the specific patterns of elements in these stars, astronomers can infer the masses and properties of the population 3 stars that enriched the gas from which they formed. Finding these ancient stars is challenging because they are rare, faint, and scattered throughout the halo. Large-scale surveys systematically search for stars with unusual colors or spectral properties that might indicate low metallicity. When candidates are identified, detailed spectroscopic analysis can measure the abundances of dozens of elements, creating a chemical fingerprint that reveals the star's formation environment and age. Some of the oldest known stars are nearly as old as the universe itself, perhaps 13 billion years old or more. These stars were forming when the universe was less than 1 billion years old, when the first galaxies were just beginning to coalesce from the primordial dark matter halos. The oldest stars tend to be low-mass red dwarfs, because these stars have main sequence lifetimes exceeding the current age of the universe. A red dwarf with a mass of about 1/10 the Sun's mass can sustain hydrogen fusion for 1 trillion years or more, far longer than the current age of the universe. Paradoxically, this means that every red dwarf ever born still exists today, still fusing hydrogen in its core. Not a single red dwarf has yet completed its main sequence lifetime and evolved into a white dwarf. The red dwarfs we see today, weather-formed. 13 billion years ago, or just yesterday, will still be shining trillions of years from now, long after more massive stars like the Sun have exhausted their fuel and faded away. At the other extreme are the youngest stars, objects still in the process of formation or recently born within the last few million years. These stellar nurseries exist within giant molecular clouds, vast regions of cold, dense gas where star formation is actively occurring. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, contains hundreds of young stars, many less than 1 million years old. These stars are still surrounded by the disks of gas and dust from which they formed, and many are accreting material from these disks. Observations in infrared light, which can penetrate the dust that obscures these regions in visible light, reveal protostars still embedded in their natal cocoons, objects that haven't yet completed their collapse and begun steady hydrogen fusion. Young stars often appear in associations, loose groups of stars that form together but aren't gravitationally bound strongly enough to remain together long-term. These OB associations, named for their content of hot O and B-type stars, contain the most massive and luminous stars in the galaxy. The presence of these short-lived giants reveals that star formation occurred very recently in cosmic terms. The Scorpius-Centaurus association, the nearest OB association to Earth, at about 400 light-years away, contains stars only 5 to 15 million years old. Several of these stars have already exploded as supernovae, with their remnants detectable as expanding shells of hot gas, and some scientists speculating that particles from these explosions may have reached Earth, possibly even influencing Earth's climate through ionization of the atmosphere. The youngest stellar objects, Class 0 protostars, are completely obscured by dust and visible only in far infrared and submillimeter wavelengths. These objects are still accumulating most of their mass from the surrounding envelope. As they evolve, they become Class 1 protostars with cleared polar regions that allow jets to escape. Then Class 2 pre-main sequence stars with prominent disks and cleared envelopes. And finally, Class 3 stars where the disk has largely dissipated, leaving behind a young main sequence star possibly with planets forming or already formed in the disk. This entire process takes a few million years for Sun-like stars, but observing many protostars at different stages allows astronomers to piece together the sequence of events. Young stars are often variable and active. T Tauri stars, pre-main sequence stars still contracting toward the main sequence, show irregular variability, strong emission lines in their spectra indicating active accretion and stellar winds, and frequent flares from intense magnetic activity. These characteristics gradually diminish as the star settles onto the main sequence and its rotation slows due to magnetic braking. The Sun was likely a T Tauri star about 4.5 billion years ago, far more active and variable than it is today. The intense radiation and stellar winds from young stars can affect planet formation in their disks, potentially determining which planetary systems will develop habitable worlds. The age distribution of stars in different parts of the galaxy reveals its structure and history. The galactic disk contains stars of all ages, from ancient population 2 stars to recently formed population 1 stars. Though young stars concentrate in the spiral arms where active star formation occurs. The galactic bulge contains primarily old stars formed in the galaxy's early history. The halo contains almost exclusively old metal-poor stars. This distribution indicates the Milky Way formed from the inside out, with the central regions and halo forming first, followed by the disk building up over billions of years through continued gas accretion and star formation. The ongoing process of star formation means the galaxy is still evolving, still converting gas into stars, though the rate has declined dramatically from the peak of star formation in the universe's early history. In our exploration of stellar extremes, certain stars stand out as record holders, pushing the boundaries of what stars can be. These extreme examples represent the limits of stellar physics and the extraordinary diversity of stellar properties. Cataloguing these extremes not only satisfies curiosity, but also tests our theoretical understanding of how stars form, evolve, and die. As observational techniques improve, some of these records have been broken, with new discoveries revealing even more extreme objects. But each record holder, whether current or former, teaches us something fundamental about the nature of stars and the laws of physics that govern them. The largest known star by radius is currently thought to be either Stephenson 2-18 or potentially UY Scuti, both red hypergiants with radii exceeding 1,700 times the Sun's radius. These measurements remain uncertain because these stars have diffuse, ill-defined outer atmospheres that pulsate and vary, making it difficult to precisely define where the star's surface ends. If Stephenson 218's largest estimated size is correct, its radius exceeds 2.5 billion kilometers, meaning that light from its center would take over 3 hours to reach its surface. These enormous stars exist in a precarious state, barely held together by gravity against the outward pressure of their intense radiation. They lose mass through powerful stellar winds at rates that could deplete them entirely within a few 100,000 years, creating vast circumstellar nebulae of ejected material. The smallest stars are red dwarfs near the hydrogen-burning limit, the minimum mass required to sustain hydrogen fusion. Below about 8% of the Sun's mass, or roughly 80 times Jupiter's mass, a star cannot achieve the core temperatures needed for hydrogen fusion and becomes a brown dwarf instead, an object that may fuse deuterium and lithium temporarily but never establishes stable hydrogen fusion. The smallest known true stars have masses just barely above this limit. These tiny stars have radii only slightly larger than Jupiter, making them not much bigger than large planets despite being genuine fusion-powered stars. Their small size and low luminosity make them difficult to detect, but they are by far the most common type of star in the galaxy. The most massive star known is R136A1, located in the Large Magellanic Cloud's Tarantula Nebula. This monster has an estimated mass of about 250 to 300 solar masses, though it may have been even more massive when it formed. Stars this massive were. Thought to be theoretically impossible because radiation pressure should prevent gas clouds from collapsing to such high masses. The discovery of R136A1 and similar extreme stars has challenged these theories, suggesting that very massive stars might form through collisions and mergers of smaller stars in dense stellar clusters, or that our understanding of mass loss and stellar winds in the most massive stars needs refinement. R136A1 has a surface temperature exceeding 50,000 Kelvin and radiates with a luminosity about 8 million times the Sun's output. Such extreme stars live only a few million years before exhausting their fuel and exploding as exceptionally violent supernovae, or possibly collapsing directly into black holes. The hottest stars are not necessarily the most massive. Wolf-Rayet stars, evolved massive stars that have shed their outer hydrogen layers to expose their hot helium cores, can have surface temperatures exceeding 100,000 Kelvin. Some white dwarfs, when newly formed, can also reach temperatures of 200,000 Kelvin or more, though they're not undergoing fusion and are simply radiating away their stored thermal energy. The hottest known white dwarf surfaces exceed 250,000 Kelvin. At these temperatures, the star emits primarily in the extreme ultraviolet and soft X-ray regions of the spectrum, appearing intensely bright in these wavelengths while being relatively faint in visible light. The coolest stars are the late M-type red dwarfs and the newly recognized L, T, and Y-type brown dwarfs. Y-type brown dwarfs can have effective temperatures below 300 Kelvin, cooler than the boiling point of water and approaching room temperature. These objects glow in the infrared, but are effectively invisible in optical wavelengths. They represent the transition between stars and planets. massive enough that they likely formed like stars from gravitational collapse, but too small to sustain fusion. Instead, cooling gradually over billions of years like planets. The coolest confirmed white dwarf has a temperature estimated at around 250 Kelvin, colder than any star and comparable to some solar system moons. The oldest star with a well-determined age is probably the subgiant HD 140283, often called Methuselah star. Age estimates based on its properties and evolutionary state suggest an age around 14.5 billion years, plus or minus several hundred million years. This initially caused concern because it seemed to be older than the universe itself, estimated at 13.8 billion years. However, the measurement uncertainties overlap, and refined analyses have brought the star's age estimate into agreement with cosmological age determinations. This ancient star is metal poor, confirming its formation in the early universe, and it provides important constraints on the age of the oldest stars in our galactic neighborhood. The closest star to Earth, besides the Sun, is Proxima Centauri, a red dwarf located about 4.24 light-years away in the Alpha Centauri system. Despite being our nearest stellar neighbor, Proxima Centauri is too faint to see with the naked eye, requiring binoculars or a telescope to observe. This tiny star has about 12% of the Sun's mass and 1/1000th its luminosity. In 2016, astronomers announced the discovery of Proxima Centauri b, a planet orbiting in the star's habitable zone, making it the closest known exoplanet to Earth. Whether this world is actually habitable remains uncertain, given that red dwarf flares. And stellar activity might strip away planetary atmospheres, but the discovery has made Proxima Centauri a prime target for future interstellar mission concepts. These record holders span an almost incomprehensible range. The largest stars are over 10,000 times larger than the smallest. The most massive stars are more than 10,000 times more massive than the least massive. The most luminous stars outshine the dimmest by factors of billions. This diversity arises from the interplay between mass, composition, and evolutionary state, with stars of different masses following radically different life paths. Understanding these extremes helps define the boundaries of what stars can be, and tests whether our theoretical models can successfully explain the full range of observed stellar properties across the entire Hertzsprung-Russell diagram. The universe has not always looked as it does today, and it will not always look as it does now. Stars, for all their grandeur and power, are temporary. They form, evolve, and die, and the overall rate at which new stars form has been declining for billions of years. Looking to the far future, we can predict how stellar populations will change, and what the ultimate fate of all stars will be. This cosmic eschatology, the study of the universe's end state, reveals a future both fascinating and melancholy, where the brilliant lights that fill the current universe gradually fade one by one into eternal darkness. Star formation requires cold gas, primarily hydrogen, that can collapse under gravity to form new stars. In the early universe, gas was abundant, and star formation proceeded vigorously. The star formation rate peaked around 10 billion years ago, when the universe was just a few billion years old. Since then, the rate has declined as galaxies have converted increasing fractions of their gas into stars, and as the expansion of the universe has made it harder for galaxies to accrete fresh gas from the intergalactic medium. Some galaxies, particularly massive elliptical galaxies, have exhausted most of their gas and have experienced little or no star formation for billions of years. These red and dead galaxies contain only old stars, gradually fading as the more massive members evolve and die. The Milky Way continues to form stars, producing roughly 1 to 3 solar masses of new stars per year, but this rate is far lower than it was in the past. As the galaxy's gas supply dwindles, star formation will gradually decline. Simulations suggest that within a few billion years, the Milky Way will collide and merge with the Andromeda Galaxy. This collision will trigger a burst of star formation as gas clouds collide and compress, but it will also consume much of the remaining gas, leaving the merged galaxy with limited reserves for future star formation. Within perhaps 10 to 20 billion years, most galaxies will have exhausted their gas supplies, and star formation throughout the universe will become increasingly rare. The last stars to form will likely be low-mass red dwarfs, the most efficient users of hydrogen fuel. These final stellar generations will continue forming in scattered pockets where residual gas remains until perhaps 100 trillion years in the future, when essentially all available hydrogen has been locked up in stars, planets, brown dwarfs, and stellar remnants. At this point, an era that has lasted over 100 trillion years will end. No new stars will form. The universe will contain only the stars already existing, and these will gradually run out of fuel and die. The most massive stars will have disappeared long before this point, having lived and died within a few million years of their formation. Sun-like stars will have evolved through the red giant phase and become white dwarfs. The galaxy of 100 trillion years hence will contain primarily red dwarfs, still steadily fusing hydrogen, along with countless white dwarfs, neutron stars, and black holes left behind by previous stellar generations. The red dwarfs will continue to shine for an extraordinarily long time. The smallest red dwarfs, with masses around 1/10 the Sun's mass or less, have main sequence lifetimes exceeding 10 trillion years. These ultra-long-lived stars will dominate the far future universe, slowly consuming their hydrogen reserves over timescales that dwarf the current age of the universe. Eventually, even these persistent stars will exhaust their fuel. One by one, over tens of trillions of years, the last red dwarfs will deplete their hydrogen, swell briefly, and then fade into white dwarfs. By about 100 trillion years in the future, the last conventional star will have burned out. The universe will have transitioned from the stelliferous era, the current age of stars, into the degenerate era, dominated by stellar remnants, white dwarfs, neutron stars, and black holes. The universe will be dark and cold, with only the faint glow of white dwarfs providing any illumination, and even this will gradually fade. White dwarfs will cool over trillions of years, eventually becoming black dwarfs, cold, dark remnants that no longer emit detectable radiation. The universe is currently too young for any black dwarfs to have formed yet, but given enough time, all white dwarfs will cool completely. Some models suggest this process takes tens of quadrillions of years. Neutron stars will also cool, though they start with such high temperatures that they will remain detectable longer than white dwarfs. Eventually, on timescales of perhaps 10 to the 32nd power years or longer, even protons may decay, if grand unified theories that predict proton decay are correct. If this occurs, all stellar remnants except black holes will gradually dissolve as their constituent protons decay into lighter particles and radiation. Black holes will survive longer still, but even they are not eternal. Stephen Hawking showed that black holes emit radiation through quantum effects near their event horizons, very slowly losing mass in a process called Hawking radiation. For stellar mass black holes, this evaporation takes unimaginably long around 10 to the 67th power years. For supermassive black holes, the timescale extends to 10 to the 100th power years or longer. Eventually, even the largest black holes will evaporate completely, leaving behind only a faint spray of elementary particles dispersing into the expanding void. In the ultimate far future, perhaps 10 to the 100 power years hence or longer, the universe will have reached a state of maximum entropy. All stars will have died. All stellar remnants will have decayed or evaporated, and all that will remain is a thin, cold gas of elementary particles expanding forever through an increasingly cold and empty space. No structures will remain, no complexity, no life. This heat death represents the ultimate endpoint of cosmic evolution under current physical understanding, a state from which nothing interesting can emerge. The brilliant era of stars, which has lasted perhaps 100 trillion years from the first stars to the last, will represent only a brief, bright flicker in the eternal night that follows. Yet even in contemplating this dark future, there is a strange beauty and profundity. We exist during the stelliferous era, the age when stars fill the universe and make life possible. Every moment of human existence, every thought you've had, every person you've known, all of human history and prehistory, the evolution of life on Earth over 3.5 billion years, all of it occupies an inconceivably brief instant near the beginning of cosmic history. We are fortunate to live in an era when the universe is young and vibrant, when stars blaze against the darkness, forging elements and making worlds. In a real sense, we are the universe becoming aware of itself during its most active and interesting phase, before the long fade into cold and dark. The story of stars is ultimately the story of the universe itself and our place within it. Stars are the engines of cosmic evolution, transforming the simple elements created in the Big Bang into the rich complexity we see around us. They gather diffuse gas into concentrated masses, ignite fusion reactions that power themselves for billions of years, create heavy elements in their cores, and scatter these elements into space when they die. The enriched gas forms new stars and planets, continuing the cycle. Each generation of stars builds on the previous one, gradually increasing the universe's chemical complexity. Without stars, the universe would be a far simpler place, containing only hydrogen, helium, and trace amounts of lithium. There would be no carbon or oxygen, no silicon or iron, none of the elements necessary for rocky planets or life. Stars create the conditions necessary for complexity to emerge, from molecules to planets to life. The Sun, our particular star, has been shining steadily for over 4 billion years, providing the energy that powers Earth's climate, drives photosynthesis, and ultimately sustains all life on our planet. Every photon of sunlight that warms your face, every calorie of energy in the food you eat, traces back to fusion reactions in the Sun's core. Looking up at the night sky connects us to this cosmic story in the most direct way. The light entering your eyes left those distant stars years, decades, centuries, or even millennia ago. You are literally seeing into the past, observing these stars as they were when their light began its journey across space. The photons striking your retina were created in stellar cores or atmospheres, traveled across light years of space, and ended their journey by triggering chemical reactions in your eyes that allow you to perceive them. You are directly interacting with stars that may be hundreds or thousands of light years away, connected by electromagnetic radiation that bridges the enormous distances between worlds. Understanding stars also provides perspective on humanity's place in the universe. We are not separate from the cosmos, but rather an integral part of it. The atoms in your body were forged in stellar furnaces billions of years ago. You are made of ancient stardust, recycled through multiple generations of stars before eventually being incorporated into the molecular cloud that collapsed to form the sun and planets. The iron in your blood saw the interior of a massive star and experienced the violence of a supernova explosion before ending up in your body. The calcium in your bones, the oxygen you breathe, the water you drink, all were created by stars and stellar processes. This realization transforms how we might view our relationship with the universe. We are not merely observers of cosmic phenomena, but participants in ongoing cosmic evolution. The heavy elements being created in stars today will be scattered by future supernovae and novae, enriching the interstellar medium for stars and planets that will form billions of years from now. Life on Earth, whatever form it takes in the distant future, will continue to be built from stellar ashes. If humanity survives and spreads beyond Earth, we will carry stardust with us to other worlds, extending the reach of materials processed through stellar nucleosynthesis. The study of stars also humbles us by revealing our cosmic insignificance, while simultaneously elevating us through understanding. Individual stars like the Sun are unremarkable among the hundreds of billions in our galaxy, and our galaxy is itself unremarkable among hundreds of billions of galaxies in the observable universe. The sheer scale of the universe, with its trillions upon trillions of stars scattered across billions of light years of space, makes our individual lives seem vanishingly small. Yet we are also extraordinary in our ability to understand this vast cosmos. Through careful observation, mathematical reasoning, and scientific inquiry, humans have decoded the secrets of stars, understood their physics, measured their distances, and placed them within the broader context of cosmic evolution. The fact that matter can organize itself into forms capable of understanding stars, that the universe can produce conscious observers who comprehend stellar nucleosynthesis and stellar evolution, is perhaps the most remarkable fact of all. We are, in Carl Sagan's famous phrase, a way for the cosmos to know itself. The atoms in our brains, forged in long-dead stars, have arranged themselves in patterns complex enough to understand their own origins and to contemplate the lives and deaths of stars across cosmic time. This self-awareness of the universe represents an achievement as magnificent as any stellar explosion, a triumph of complexity emerging from simplicity. As our sun-like star continues its journey through the main sequence, steadily converting hydrogen to helium, warming our world and making life possible, we can appreciate both its ordinariness and its profound importance to us. In approximately 5 billion years, the Sun will exhaust its core hydrogen and begin its transformation into a red giant, potentially destroying the Earth and certainly ending any life that might remain on our planet. But this is not a cause for despair. 5 billion years is an almost unimaginable span of time, longer than Earth has yet existed, longer than life has existed on our planet. If humanity or its descendants survive even a tiny fraction of this time, we will have achieved something extraordinary. Looking forward, the future of stellar astronomy promises continued discoveries and revelations. New telescopes, both ground-based and space-based, will detect ever more distant and fainter stars. The James Webb Space Telescope is already observing some of the most distant stars ever seen, including individual stars in galaxies billions of light years away, magnified by gravitational lensing. Future missions may directly image the surfaces of nearby giant stars, revealing the convection patterns and star spots on their surfaces. Advanced gravitational wave detectors will observe stellar mass black holes and neutron stars merging throughout the universe, providing entirely new information about these exotic objects. The search for life beyond Earth is intimately connected to the study of stars. Understanding stellar evolution, stellar activity, and the conditions around different types of stars helps astronomers identify which stars are most likely to host habitable planets. Red dwarfs, the most common type of star, are receiving increased attention as potential hosts for life because their long lifetimes provide billions upon billions of years for life to emerge and evolve. However, their intense flare activity may pose challenges for atmospheric retention on close-in planets. K-type stars, slightly cooler than the Sun, may represent a sweet spot. They're less active than red dwarfs, but longer-lived than Sun-like stars, potentially providing the most favorable conditions for life. As we continue exploring the cosmos, discovering thousands of planets around other stars, characterizing their atmospheres, and searching for biosignatures that might indicate life, we will need increasingly sophisticated understanding of their host stars. The properties of a planet are intimately tied to the properties of its star. The star's luminosity determines where the habitable zone lies. The star's spectrum affects the planet's atmospheric chemistry. The star's activity influences the planet's atmospheric retention and surface radiation environment. Understanding stars is thus essential to understanding planets and, ultimately, to answering the profound question of whether we are alone in the universe. The stars that fill our night sky, that have inspired wonder and myth throughout human history, that guided ancient navigators and prompted humanity's first astronomical observations, are now understood in remarkable detail. From the nuclear physics of their cores to the fluid dynamics of their convecting envelopes, from their formation in molecular clouds to their ultimate fate as white dwarfs, neutron stars, or black holes. From the smallest red dwarfs to the largest hypergiants, we have mapped the full diversity of stellar properties and evolution. Yet, for all we have learned, mysteries remain. The exact mechanisms triggering star formation, the details of convection in stellar interiors, the origins of stellar magnetic fields, the nature of matter in neutron star cores, the formation of the most massive stars, all present ongoing challenges that will occupy astronomers for decades or centuries to come. Each time you look up at the stars, you are witnessing something profound and ancient. The light from those distant suns has traveled across the vast emptiness of space, carrying information about objects so remote in space and time that they might as well inhabit a different reality. Yet, they are connected to us through the universal laws of physics, through the chemical elements they've created and that we are made of, and through the electromagnetic radiation that bridges the distance between their worlds and ours. They are both impossibly distant and intimately familiar, both alien and kindred. They represent our past, the crucibles that forged thee. Atoms we're made of, and potentially our future, the destinations we might someday reach if we survive long enough to become a star, faring civilization. The universe of stars is a universe of almost unimaginable scale and diversity, of violence and beauty, of birth and death played out over timescales from microseconds to trillions of years. Understanding stars is understanding the universe itself, and through that understanding, coming to know our place within the grand cosmic story that began with the Big Bang nearly 14 billion years ago, and will continue until the last stars fade and darkness claims the cosmos. We are fortunate to exist in this brilliant age, when the universe blazes with the light of countless stars, when complexity has emerged from simplicity, when matter has become conscious and turned its gaze outward to comprehend the very stars from which it came. This is the legacy of stars. Not merely light and heat, but understanding, awareness, and the profound realization that we are, and have always been, children of the stars. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.